In this lecture, we are going to talk about inverse trigonometric functions and their derivatives. So essentially, more formulas, more functions that we know, we can find their derivative, and so also more functions that we can find antiderivatives. First, let's review what inverse trigonometric functions are. So we define sine inverse of x to be the inverse function of sine. This is the sine function, which is not one-to-one. So we can't really define an inverse function of the whole sine. Instead, we choose a piece of the graph that is one-to-one. So instead of taking the whole thing, we take the red piece so that it's one-to-one. Okay, and this red piece is between negative pi over 2 and the positive pi over 2. Similarly, we do the same thing for cosine. Okay, so from 0 to pi. And for tangent, the choice is very natural. This piece from negative pi over 2 to pi over 2. This is the reason when we talk about the inverse functions, we are choosing our range to be, essentially these for each of them. We choose those angles to be nice and include the natural first quadrant from 0 to pi over 2. Essentially, that's the reason. We want the nicest piece from 0 to pi over 2. And meanwhile, we extend it to negative if we can, because it's symmetric, it's nice. But when we can't, which is the cosine case, we extend the other way, go to pi. Still some reviews of the inverse trig functions. How to find the inverse trig function of a value, say sine inverse of 1/2. Call it y. Then we know sine y equals 1/2. Sine y is positive. Remember, essentially when the angle, if the ratio is positive, we choose from quadrant 1, and when the ratio is negative, we choose from quadrant 4, which make it negative. So we are here, quadrant 1. In quadrant 1, we know that this is our y with the opposite over hypotenuse is 1 over 2. What is this angle? Well, that's our special triangle. Y equals the 30 degree or pi over 6. Second example, we want to find cosine of tan inverse of negative 1/2. So first of all, when I give you negative 1/2, which is a ratio, I ask you to find tan inverse of negative 1/2. So which angle has tangent value negative 1/2? And then I ask you, okay, we found that angle. What is cosine ratio? Okay, so this is our angle, and we call it y. So let y be tangent inverse negative 1/2, which means tan y equals negative 1/2, and our y is in quadrant 4. Negative 1/2 in quadrant 4 has to be positive x and negative y. So positive x and negative y, this way. And from Pythagorean theorem, we know that the hypotenuse will be square root of 5, and that tells us the cosine of tan inverse negative 1/2. Again, this is y, is the cosine y. You have placed the y in its standard position, and you have all the three sides, x, y, and r. So cosine is adjacent over hypotenuse, or x over r. I don't really ask you to rationalize it. You can leave it as 2 over radical 5. Or if you want to, you can rationalize it, but you don't have to. Okay, next example, we are going to look for, again, I give you this x, which is a ratio. We know that some angle has tangent value as x, and we ask, what is the sine ratio of the same angle? But this time the problem is I didn't tell you whether x is positive or negative, which means you don't know the angle tan inverse of x sits in the first quadrant or the fourth quadrant. How can we do it? We just discussed the two cases, starting from the positive. If x is positive, well, our y will be tan inverse of x anyway, and that means tan of y equals x, or I need two sides, tan over 1. When it's positive, we are in quadrant 1. I don't want to say q1, 0, pi over 2. So my tangent y is x, opposite over adjacent. Then my hypotenuse will be 1 squared plus x squared, or 1 plus x squared. So my sine y, or sine tan inverse of x, is actually opposite over hypotenuse, x over square root of 1 plus x squared. Now, if x is less than 0, my y will still be tan inverse of x, but this time I'm in quadrant 4, negative pi over 2 to 0, and here it is. My tan y will still be x, but this time my x is negative, which will be the y, and my x coordinate is positive. It's still x over 1. Then my hypotenuse will still be square root of 1 plus y squared, and my sine y, or my sine tan inverse of x, is still the opposite over the hypotenuse. It's just that this time the opposite is negative. So no matter when x is positive or negative, my sine of tan inverse of x has the same expression in terms of x. So we know that sine of tan inverse x is x over 1 plus x squared, regardless of whether x is positive or negative. Okay, now you can try practice number 1 and number 2. All right. Here we have a bunch of derivatives of our inverse trig functions. So the derivative of sine inverse is 1 over square root of 1 minus x squared. The derivative of cosine inverse is negative 1 over square root of 1 minus x squared. And tangent inverse has derivative 1 over 1 plus x squared. I'm not going to show you how we obtain these formulas, but essentially it involves what we just did. Anyway, yeah, I don't want to prove it to you, but I want to get your attention on the domain. For the original function f, which is sine inverse function, or g of x, which is cosine inverse function, you can have the inverse value evaluated at -1 or +1, because if you look at the graph, we know that sine inverse of +1 give you pi over 2, and sine inverse of -1 give you negative pi over 2. But these 2 points, you don't have derivative, because, if you look at the formula of the derivative, plugging in 1 give you 1 over 0. Or if you look at the graph, they already tend to the end. So it's not differentiable over there. Okay, that's why while the domain of sine inverse and cosine inverse are -1 to 1, endpoint included, the domain of the derivatives turns to -1 to 1, endpoint not included. So this is another case where the domain of derivative gets smaller than the domain of the original function. All right, having these formulas, we can find the following derivatives. First, cosine inverse of 2x. So the formula we have is sine inverse of x, cosine inverse of x, tangent inverse of x. When what sits in x is not x itself, it becomes, like sine inverse of u, then it will be u squared times u prime, or u squared times u prime. That's the chain rule. So in particular, question 1, we are having a little chain rule. F prime of x will become -1 over 1 minus x. The input of cosine inverse becomes the input of cosine inverse, which is 2x squared. What's supposed to be x is not really an x, so you follow by its derivative. This gives you -1 over square root of 1 minus 2x squared to 2 squared x squared, 4x squared, times the derivative of 2x is just 2. So this gives me -2 over square root of 1 minus 4x squared. A chain rule. Second example, y equals x times sine inverse of x squared. So this y actually at the end is a product of x and sine inverse. So we need to use product rule. dy dx is x times sine inverse x squared, the whole thing derivative, plus I'm keeping the whole thing the same way, times x derivative. Let me put the parentheses. So the first part is a chain rule, sine inverse of x squared instead of x. So we do exactly what we just did. Plug in the formula of the derivative, x squared, squared again, times the derivative of the input of sine inverse, plus the second part, the derivative of x equals 1. So the whole thing just disappears. All right, and here the derivative of x squared is 2x. Well, I'll write it here. Equals 2x, right? So you have x times 1 over 1 square root of 1 minus x to the 4th power times 2x plus anything times 1 is itself. So sine inverse of x squared. Finally, I just put pretty much them together on the same numerator. I'm having 2x squared over square root of 1 minus x to the 4th plus sine inverse of x squared. Now you can try to do practice number 3 and number 4. More formulas. Integral, as you can see, sine inverse and tangent inverse have very nice derivatives, which are these two. So when you have some integrand which looks like 1 over, essentially a number plus x squared, or square root of a number minus x squared, these are like the candidates where you can try to turn them into sine inverse and tangent inverse by finding their integral. Or in general, when you have square root of a squared minus x squared, or a squared minus plus x squared, no square root, they can be, you can find their antiderivative by using the formulas of these two. Personally, I don't really remember these two formulas as formulas because they are huge. For me, I remember the formula of 1 over square root of 1 minus x squared and 1 over 1 plus x squared, and I do little substitution. So for example, which one is easy to do? Let me do the second one. So when I have the integral of 1 over x squared minus, the integral of 1 over a squared plus x squared dx, I want this to be 1. So what I would do is I will factor out a squared. Then I'm having 1 plus x over a squared, x over a squared dx. Then I pull my 1 over a squared outside, 1 over 1 plus x over a squared dx. And obviously my u will be x over a. Then my du will be dx over a, or dx equals a du. Then I'm having 1 over a squared, 1 over 1 plus u squared, dx is a du. And a get cancelled. I'm having 1 over a, the integral, let me write it again, 1 over 1 plus u squared du, which is tan inverse, equals 1 over a tan inverse u plus c, where u is actually x over a plus c. Okay, so just get the one that you need in the formula by pulling out whatever the coefficient or whatever the constant is, and then change of variable. But of course, if you can remember the formulas, remember the math formulas. For me, substitute is easier than remembering two more huge formulas. Okay, keep that in your mind. So pretty much our goal is to get, if you have a square root, 1 minus x squared. If you have no square root, 1 plus x squared, or more like 1 minus u squared and 1 plus u squared. Okay, so whatever sits there, you want the square root of it to be u. Well, anyway, let's do example for integrals. This is the straightforward case. I pull out my 4 and having 1 over square root of 2 and 1 over 2 as limits 1 over square root of 1 minus x squared dx. That is formula ready. So this is sine inverse. Okay, this is sine inverse. Evaluated from 1 over 2 to 1 over square root of 2. So it's 4 sine inverse 1 over square root of 2 minus sine inverse 1/2. Okay, they are both positive in quadrant 1. I'm having opposite over hypotenuse, and I'm having opposite over hypotenuse. This is 1 radical 2, this is 1 radical 2, 3. So 45 degree and 30 degree in radian measure would be 4 pi over 4 minus pi over 6. So this is pi times 12, 3 pi minus 2 pi. So we have, oh sorry, I meant 4 here. So we have 4 times pi over 12 or pi over 3. This is why, finding the inverse of trig ratios are important. When our 1 over square root of 1 minus x squared or 1 over 1 plus x squared turn into sine inverse and tangent inverse, you need to be able to find the value. Next example, we are looking for the integral of this fraction. So, well, if it was reversed, flipped, 2 terms over 1 term, we can easily say separate the fraction into two single fractions, which turn out to be powers of e. But of course, we don't have that. So you are going to observe that you are having like 1 plus x squared situation. So let u to be e to the x because I want u squared here. Okay? So instead of having e to the 2x, I take e to the x. Not only that, but also when I do that, this is my du. Oops. Don't see that? du dx is e to the x or du. Well, the other way around. ex dx is du. So not only that, I took care of the denominator, but also the numerator will be absorbed. The numerator will just be the derivative that comes out from u. I'm dealing with definite integral. I need to change my limits. X equals 0, u is e to the 0th power, which is 1. X equals 1 goes to u equals e to the first power, which is e. Then my integral becomes from 1 to e. Ex dx is the du over 1 plus u squared. Nice tangent inverse formula u. Evaluated from 1 to e. So I'm having tan inverse of e minus tan inverse of 1. E over 1, I have no idea, but 1 over 1, I know that's 45 degree. So I have tan inverse of e remain the same way minus 45 degree in radian pi over 4. Okay, that's how you sort of combine the substitution rule, the derivative of e to the x, and also the integral of tan inverse together. Okay, try practice 5 and 6, but here I have the remark for you. We only talked about sine inverse, cosine inverse, and tangent inverse. There are also cotangent inverse, secant inverse, and cosecant inverse, right? The thing is, cotangent inverse, well, we sort of define it the same way as cosine, because the graph looks like this. Again, we want the piece with 0 to pi over 2, which will extend to 0 to pi. So this is okay, we didn't talk about it, but it comes out nicely as the other three functions. Let me box this off. We can define its inverse function, and we do have its derivative, which is pretty much the opposite of tan. So, that's it. But the choices of secant and cosecant is not really universally agreed. Okay, like mathematicians don't really agree on which branch should be cosecant inverse and secant inverse. That's why I try not to talk about it. Well, in general, we don't talk about it. And when textbooks do define them, different textbooks might define them differently. Okay, so that's why I don't see secant inverse and cosecant inverse here. And the other thing is sometimes the notation, the inverse function sometimes is confusing as the exponent. So because we use cosine squared, right, as cosine x squared. So this place is where we place the exponents. So sometimes -1 as inverse gets people confused. In that case, we also have another notation. So instead of saying sine inverse, we say arc sine. Okay, well, arc sine x. So it's like backward. Or cosine inverse is arc cosine. If you see that notation, please be aware that's just the inverse function of the trig. I'll try to avoid it. I mean, since I have introduced everything in inverse, so I probably will stick with my -1 as my inverse notation. But be aware. Arc sine means sine inverse. Arc cosine means cosine inverse. Yeah, that's it for this lecture.